Okay, so this is a review for Chapter 21 on enzymes, general characteristics of enzymes, why enzymes are vital in body chemistry. Well, enzymes are biological catalysts. They also are proteins, so everything you remember from the chapter on proteins is applicable to this chapter on enzymes. They speed up reactions in the body that would otherwise never form products. So without enzymes catalyzing these reactions, life would be impossible. This is referred to as a reaction diagram. So this is energy, and this is the progress of the reaction. So this here would be the average energy of the reactants. And of course, in enzymology, we refer to these reactants as substrate. So I'll just put an S here for substrate. And let's say this is an exothermic reaction. So the products have a lower energy. And you might think, oh, well, we just go from reactants. We just go from reactants here down to products. But instead, there's actually a barrier between these two, and this is referred to as the activation energy. Actually, I'm going to use a different color here. So activation energy is essentially the height of that barrier, and when reactants go on to form products, they have to gain energy. Usually that energy comes from the collision of the particles, of the molecules, and then once they get to the top here, they can go on to form products. So this activation energy is a barrier for reactants to become products, and essentially the height of this activation energy, or the magnitude of this activation energy, is what governs the rate of a reaction. So I'll say activation energy governs the rate of a reaction. So the higher the activation energy, the slower the reaction. Now if we add a catalyst lowers that activation energy. It doesn't change the nature of the reactions and products, so they're the same, but with a catalyst, so here plus catalyst, we have a lower EA is what's symbol given for energy of activation, or activation energy. So plus a catalyst, we have a lower EA and a faster reaction. The typical ending for enzymes, the enzyme ends in ase, or sometimes in. So example, we have amylase, or we have pepsin. Identify components of the expression. E is enzyme. S is a substrate, and the substrate is essentially the reactant again. ES is this complex, this enzyme substrate complex. P, of course, is product. And E, again, is the free enzyme. And a couple of things to note here. First off, in this series of reactions, enzyme binds the substrate to form this ES complex. The substrate now bound to the enzyme in what we refer to as the enzyme active site is where the reaction occurs, and the substrate is converted to product. And then the product is released, and we end up with a free enzyme. This free enzyme then, right, can go back and bind more substrate, so the process, the cycle continues again. So the thing here about the enzyme is, and actually the thing about all catalysts, is they participate in the reaction but not changed by the reaction, so it can continue to bind more substrate and carry out that reaction. The other thing to note here is this ES complex forms an equilibrium. So what happens is the enzyme can bind the substrate, form the complex, and then the substrate can come off sometimes. And so it kind of goes back and forth, and this is important when we start talking about inhibition. So this ES complex exists in equilibrium. It exists in equilibrium with the enzyme and the substrate, so it can bind and come off, and bind and come off. Alright, now there are two main models for explaining how enzymes work. One is the lock and key, one is the induced fit. The lock and key theory or model emphasizes, maybe more of a model than a theory, emphasizes specificity. That is to say, enzyme will bind one substrate, so the lock is the enzyme, and the substrate is the key, and the key fits into the lock, and only one key will fit into that lock, so it emphasizes specificity. Whereas the induced fit theory addresses how enzymes actually speed up reactions, so how enzymes catalyze reactions. And the idea here is that the active site for the enzyme is a little loose, a little sloppy, but once the substrate binds, it induces a change in the shape of that active site, and that change in the active site stresses bonds and forces the substrate to be converted into the product. So the induced fit theory addresses how enzymes catalyze reactions. I'll say a loose active site binds the substrate, and a change in the structure. The book will tell you it's a change in the structure of the active site, but also there's a change in the structure of the substrate as well. Change in the structure of enzyme and substrate drives the reaction. And I just say here by stressing or straining or bending, twisting bonds. The ingredients for enzyme active site, we didn't talk about this in class, but naturally, of course, you're going to have, this is where the substrate binds. And the other thing that you'll find in active site, of course, is something called a coenzyme. And I was going to wait until the next unit where we talk about specific coenzymes, but I'll give you a list here. We have NAD, FAD, and coenzyme A, so we just call it CoA, or also maybe a prosthetic group. So remember, a prosthetic group is a molecule that is not protein but is required for function. So these are the types of things you'll find also in the enzyme active site, or other molecules that are required for function but are not actual amino acids. All right. Factors that affect enzyme activity. So these are now graphs. We have activity on the right, and down below here this will be substrate concentration. So this is a substrate concentration, and the enzyme activity goes up and then it levels off. We talked about Vmax, the maximal velocity, and we also talked about the concentration that will give you 1/2 Vmax, that substrate concentration that gives 1/2 Vmax, is called the Km. So this is 1/2 Vmax. That Km value is a measure of how tight or how well the enzyme binds the substrate, whereas Vmax is the maximal rate at which the enzyme can work. We know that at Vmax, we have so much substrate around that all the enzyme is bound up with the substrate, so we can say here the enzyme is saturated with substrate. Enzyme concentration curve is going to look a little bit different. Again, we're going to have activity or rate of the reaction, activity, or the rate or speed of the reaction here, and down here we have the enzyme concentration. And for the enzyme concentration, obviously we have no enzyme, the activity will be 0, and it goes up in a 1-to-1 ratio. What I mean by that is if we double the enzyme concentration, the rate doubles. If we triple the enzyme concentration, the rate triples. So the slope of this line, for the mathematically inclined, the slope of this line is 1. All right. Temperature effect. And while I have this out, I'll do pH as well. Okay, so we're following temperature and activity, or the rate of the reaction again. And what you see for most enzymes, there is a optimum value, and this is generally, for humans at least, it's 37 degrees C, because we're warm-blooded. We have a constant body temperature of about 37 degrees Celsius. Above this temperature, activity starts dropping off, and what we end up getting here is denaturation. And this is irreversible. We talked about in the chapter on proteins how once you heat up an enzyme so much it precipitates, it comes out of solution, and the enzyme is dead. It will not go back even if you cool it back down. However, down here where we've cooled it down to, let's say, 5 degrees C, this is reversible. So I'll put little arrows here, goes backwards, but this is irreversible. Once you denature that enzyme, it's dead. But you can cool it back down and warm it up, and cool it back down and warm it up, so long as you don't freeze it. Remember I said if you freeze it, if ice crystals form, that tends to denature the protein. All right, now for pH, we also see this kind of bell curve. Okay, this is activity and pH. So let's say this is pH 7, 6, 5, this is pH 4. Okay. So for a lot of enzymes, again, you will see a bell curve, something like this, where the pH optimum, the optimum pH is about 7.35, and that's because physiological pH, or the pH of our blood plasma, is 7.35. But as I stressed in class, it kind of depends on where that enzyme is. If it's not a soluble enzyme in our blood, maybe it's pepsin, and the pH optimum for pepsin is probably around pH of 2, because it's a digestive enzyme in our stomach, so it has a pH optimum that is acidic. Or we could have one that is a basic pH as well, so maybe this is like trypsin, spelled that wrong, but trypsin pH optimum is about 8.5. Actually, I have it closer to 9 here, but in any event, the actual optimal pH is kind of dependent upon the individual protein and the environment in which it works. If you get too high of a pH, that can denature the protein, and if it gets too low, it can also denature the protein. And of course, once you denature the protein, it's dead. It's a irreversible, non-reversible process. All right, compare the mechanism of competitive and non-competitive inhibition. Competitive inhibitors bind to the active site. Therefore, they must be structurally related to the substrate, which also binds the active site. So these two guys, the inhibitor and the substrate, are competing for the same site. Non-competitive inhibitors bind to an allosteric site. They use this term allosteric site. This simply means other site, a site other than the enzyme active site. Therefore, they are not structurally related to the substrate. They can be, but they don't have to be, because they're not binding the same place. They don't need the same types of interactions as a substrate. Both of these are reversible, competitive and non-competitive inhibition. These are reversible. Okay. Reversible and irreversible inhibition. All right, so reversible, we have the competitive and non-competitive. So the enzyme binds the inhibitor and forms an enzyme inhibitor complex, and this can go back the other way, and now maybe the enzyme binds the substrate. Enzyme binds the substrate and forms an enzyme substrate complex. So this is reversible. It can bind and come off and bind and come off. Let me actually make another slight addition to this. In competitive, we've got the enzyme here. If it binds the inhibitor, we form this EI, this enzyme inhibitor complex, and no substrate can bind. So we can add substrate here, nothing happens. So the competitive inhibitor, the inhibitor here is binding the active site in the enzyme, which means the substrate can't bind it. So this is inactive. Okay? In a non-competitive, so this is competitive. In a non-competitive fashion, what does this mean? Well, the enzyme can bind the inhibitor, and then there's a couple of different ways. We talked about the K-type and the V-type. The K-type is actually going to be similar to this. The K-type meaning it affects the Km, it affects the affinity or the ability of the enzyme to bind the substrate, just as it does in competitive. But in the V-type, what happens is you get this enzyme inhibitor complex, right, and that's reversible as well. But you could also add the substrate here, and you could have actually the enzyme binding to the inhibitor, and then also binding the substrate. So you have this enzyme inhibitor substrate complex where all three are bound together, but this is inactive because that inhibitor doesn't block the binding of the substrate. The substrate's still able to bind the enzyme, but the reaction doesn't occur. Why is that? Well, maybe the inhibitor causes some other change in the enzyme active site, so it doesn't affect the binding of the substrate, but some reactive side chain group of an amino acid is swung out of the way, so it doesn't participate in the reaction. The reaction doesn't work. Allosteric control, this is that non-competitive inhibition that we were talking about. And it can either be an inhibitor, or I mentioned before, it can be an allosteric activator and actually speed up the reaction. Allosteric activator. This actually speeds up the enzyme. Of course, the enzyme catalyzes the reaction anyway, but this makes it go even faster, an allosteric activator. In this section of your text, they also talk about feedback control. I'm going to put here feedback control only because if you read your textbook, you'll come across this term, and I'm going to tell you, just wait on this. We'll talk about this in a chapter on metabolism. So I'll say here, wait for metabolism. So we did not talk about feedback control as a type of allosteric control or allosteric regulation. De novo synthesis is making enzymes new, so this is that translation process. Simply making new protein, or what we call translation, or if you wish, protein synthesis. And the thing about this is it's slow, it takes a while. Zymogen activation, though, is it's fast. So this is a proteolytic cleavage, so we're breaking a peptide bond to release what the heck? Oh my god, what just happened? That was weird. So de novo zymogen activation, proteolytic cleavage releases what we call the pro sequence. A zymogen is also the same thing as a proenzyme or a proprotein. It releases a pro sequence, and this activates the enzyme. So the zymogen itself, the zymogen or this proenzyme, is inactive. Along comes another enzyme that cleaves off this proteolytic cleavage, breaks a peptide bond, releases a pro sequence. Maybe that pro sequence is a length of amino acids that's covering up the active site, and once that is released, the active site is available as it's revealed to the substrate. Now the substrate combined and enzyme can work. And the thing about zymogen activation is it keeps potentially harmful enzymes inactive until they're needed. And it allows for rapid response and an amplified response. Amplified response, as we saw with the clotting cascade, the blood clotting cascade. Discuss the importance of measuring enzyme levels in diagnosis and disease. Here we are talking about isozymes, or if you wish, isoenzymes. These are enzymes that catalyze the same reaction So maybe have two different enzymes. We talked about salivary amylase or pancreatic amylase. There are two actually different enzymes. One is excreted from your salivary glands, one is excreted from your pancreas. So they catalyze the same reaction. That's what's the same about them, but they're different enzymes. So what does that mean? They come from different genes. In some tissue types, one type might be expressed. In another tissue type, a different isozyme will be expressed, although they catalyze the same reaction. So we'll say differential tissue expression. differential tissue expression, and it also means that they have similar, very similar, because they carry out the same reaction, bind the same substrate, release the same products, but they have different primary, secondary, and tertiary structures because they're actually different enzymes, different proteins. Now, the importance of this is that when tissue is damaged from some disease process, a physician can tell what tissue is damaged, and to the extent by looking at the levels of these different isozymes or different isoenzymes in the blood. So, can be used to diagnose disease which tissues are damaged and to what extent by determining which isozymes and what their level is, which isozymes and concentrations in the blood. Alright, the general function of cofactors. I did talk briefly about cofactors. These are small molecules or ions that are required for enzyme function. Okay, example could be like the magnesium ion, or the iron ion, or maybe cobalt. So a small ion like that, or it could also be some small molecule, such as maybe ATP. ATP, maybe you don't think that's that small of a molecule compared to some that we've talked about, but compared to the enzymes or proteins, yeah, they're quite small. Or maybe a phosphate ion or something like that. Okay. We did not talk about the role of vitamins, but vitamins are precursors to coenzymes, and I did mention this right at the end of class. Right? What are coenzymes such as NAD, FAD. There's others, but we're only going to talk about 3. And coenzyme A, so CoA. So NAD, FAD, CoA. So niacin is a precursor to nicotinamide adenine dinucleotide, this NAD. Riboflavin is the precursor to flavin adenine dinucleotide, and this other enzyme called pantothenic acid is a precursor to coenzyme A. In any event, these coenzymes are also required for function, but they're larger, they're not small molecules, they're a bit larger, and they're organic, they're not inorganic ions like this. So the key thing here is they're organic, non-protein of course. They're also required for function. And the reason I don't talk about this here is because they're really not enzymes. They're really more of a co-substrate. Although the name, I don't know, they bind the enzyme at the active site and they're converted in the process of the reaction, so they're not really an enzyme. So, not a coenzyme per se. They're rather more like a co-substrate. Give you an example. Alcohol, I won't write the structure, but alcohol is oxidized to acetaldehyde. It's carried out by this enzyme called alcohol dehydrogenase. When we talked about that, when we were talking about competitive inhibition and the antidote for ethylene glycol poisoning. Well, This is an oxidation, right? Alcohol converted to an aldehyde, that's an oxidation. Well, for every oxidation there must be a reduction. And so what happens is this enzyme, this coenzyme NAD, is reduced to NADH. So you notice here it's subtle, but it gains a hydrogen. That's a reduction. It goes from a plus charge to neutral, right? So from +1 down to 0, it's neutral. That's a reduction. So the alcohol is oxidized to the aldehyde. The NAD is really a co-substrate. It gets reduced from NAD to NADH. Some of these other numbers we already talked about. IU stands for International Unit. We're not going to talk about that. The turnover number, we talked about this. Turnover number is simply the number of catalytic cycles going from empty enzyme plus substrate to the ES complex to the free enzyme again and release of the product. And how many times that this cycle occurs per unit time. It's usually per minute or per second. And that's the turnover number. Active site, of course, is where the substrate binds or where a competitive inhibitor binds and where the reaction takes place. Km, again, is a measure of how well the enzyme binds the substrate. And if you remember, it's really the substrate concentration that gives 1/2 the Vmax, 1/2 the maximal rate. So the tighter or the better the enzyme binds, the less substrate it needs. So the smaller the Km, right, that means the lower the concentration of substrate required. So the better the enzyme binds substrate. Isozyme and expression are kind of related, these two terms. Okay, we talked about this differential expression. What this means is some tissues will, a cell contains your entire genome, but not all the genes are turned on at any one time. This differential expression is what makes the difference between, say, a blood cell and a liver cell and a kidney cell and a muscle cell. They all contain the same DNA molecule, right, your entire genome, but some genes are turned on, which means some are expressed and some are expressing this protein, others are not. So expression means, I just say, a specific cell or tissue type. We use the term expresses, that is to say, or makes a specific I shouldn't say specific, makes specific types of proteins, while other different tissue types make different types of proteins. In some cases, those proteins might do the same job. Right? In metabolism, all these cells have to carry out the same metabolism. They all have to carry out this Krebs cycle, for example, but the enzymes that are responsible for that might be different depending upon which tissue type you're looking at, and that's where these isozymes come into play. Again, we talked in much more detail in lecture than we did here in this review, but hopefully this will give you something to help you on the test